Hello students, so this is our third lecture in the series of the complex lectures, and the topic for today's lecture is asynchronous counters. So these are the contents: concept of counters, what are counters, and counters with mode equal to 2 raised to the power n, counters with mode not equal to 2 raised to the power n, and we may further go into the details of the various counters which can be designed from these counters, like up down counters as well. So concept of counters. What are counters? So if I'm designing a counter, it will be counting, but what it will be counting? So it will be counting the number of clock pulses that will be entering the circuit. We are very much aware that counters will be made of flip-flops, and flip-flops cannot work in absence of clock. So the number of clock pulses that will be entering the flip-flops is a structure of flip-flop which is termed as counter. The number of pulses that will be entering that structure, flip-flop structures, it will be counted and it will be displayed in binary format at the flip-flops output. So this is counter. So now the counter can be in up mode and down mode. So if it is in up mode, we will be saying that it is in counting operation, and if it is in down mode, we will say it is in timer operation. So up mode means 0, 1, 2, 3, 4, 5 and up till where the maximum counting can be performed. And similarly, for down counting, it will start from the maximum counting that is possible and it will go down to 0. Okay. So types are asynchronous counters and synchronous counters. So we have discussed in the very first line in the when I said that counters are counting the clock pulses and it is made up of flip-flops. So if all the flip-flops are having a single clock, that is the clock is common to all the flip-flops, then those counters are known as synchronous counters. Okay. And if all flip-flops have separate clocks and external clock is provided only to one of the flip-flops and rest of the flip-flops are getting their clocks from somewhere else, maybe from some other flip-flop connections, maybe from some other flip-flops outputs, then in that mode the counter will be termed as asynchronous counter. Okay. So we can say that in synchronous counter, either all flip-flops will work or none will work, because clock will be provided to all the flip-flops simultaneously. So now let's proceed to the details of these asynchronous counters. So asynchronous counters, so if we are interested in designing a mode and counter, mode and asynchronous, so first of all we will be very much aware that what is mode of a counter. So mode means the number of stages that the counter will be going through. So if I'm saying that my counter will count from 0 to 7, so 0, 1, 2, 3, 4, 5, 6, 7. So there are total 8 stages. So the counter which will be counting from 0 to 7 is having 8 stages. So the mode of the counter will be 8. That's why mode 8 asynchronous up counter. Up counter, why? Because it is counting from 0 to 7. Similarly, if it is counting from 7 to 0, then it will be mode 8 asynchronous down counter. Okay. So this is all about mode, and mode is also known as modulus, which is the number of unique stages offered by counter. That means mode and counter is also known as divide by n counter, because the frequency, the input clock frequency which is being applied at the LSB flip-flop, which we will be seeing when we will be designing the circuit, that the resultant frequency at the last flip-flop is actually 1 by nth of the clock pulse frequency which is being applied at the beginning. So this will be checking later on. Number of flip-flops required, most important question. So if we are designing a counter, so how many flip-flops will be required? I have to check that how many the counter will be counting up till which state. So if I'm saying that my counter will be counting up to 7, so 7 means 111 in binary. 111 in binary means that means 3 bits are required. So for 3 bits, I will be requiring 3 flip-flops. Okay. So type of clock. Now there is some constraint that if you use particular type of clock, you will be counting in particular operation, particular mode. So the basic idea is, if I'm using in negative edge triggered clock, then I will be in up mode, and if I am using positive edge triggering, then I will be counting in down mode. Although these are interchangeable, if I make some alternative clock connections that we will also see. But for the timing, you can remember as if you are asked to design a up counter specifically, then we will be using negative edge, and if we are asked to prepare down counter specifically, we will be using positive edge. Only T flip-flop can be used. Another important point. It is not the case that I can use any flip-flop, D, SR, JK, but my requirement is T flip-flop, although that is very much clear to me that I can easily design T from JK. So if I'm asked to design a counter using JK flip-flop, then it is not a concern for me, because I will simply connect J and K and it will become T flip-flop. So next thing is all T inputs will be connected to logic 1. That means if I am having 3 T flip-flops in my counter circuit, then the T input of all the flip-flops will be connected to a common point and it will be connected to logic 1. That means all T flip-flop inputs are 1. That means all the flip-flops are in toggling mode. That means they are just waiting for the clock pulse to arrive and they will toggle the output. Okay. So if the output of the flip-flop is 0, it will become 1. If it is 1, it will become 0. Permanently, T is equal to 1. That means it is just waiting for the clock pulse. If it will get the clock pulse, it will definitely toggle the output. If it will not get the clock pulse, it will remain in its previous state. Okay. So dedicated clock is provided only to LSB flip-flop. As we have discussed in the concept of asynchronous counter, that clock will be provided only to one of the flip-flop. And which flip-flop it will be? The flip-flop which will be generating the LSB of the counting, least significant bit of the count. Then how the other flip-flops are going to get the clock? So other flip-flops will get their clock from previous flip-flops outputs. Okay, so they will be getting the output from clock connection from the previous flip-flops output. So let's start designing the counters now. So mode 8 asynchronous up counter. So mode 8 means 8 stages. So what are these 8 stages? 0 to 7. So if I write it in binary, so 000 to 111. Okay. So 111 means 3 flip-flops are required. Which flip-flops are required? T flip-flops are required. So I have taken 3 T flip-flops. And then I have mentioned that if I need to perform up counting, then I will be using negative edge triggered flip-flops. So these are negative edge triggered flip-flops. So this is the symbol of negative edge triggered flip-flop. So 3 T flip-flops are there. Then here we can see that LSB is marked. That means this is the flip-flop where I am going to apply my clock pulse, and not just clock pulse, clock pulses. That means all the clock pulses which are going to be provided externally, which are going to be counted, are going to be applied on the clock of this LSB flip-flop, which is being marked as TA. Okay. So here I will provide my external clock. Okay. External clock will be provided here. All T inputs are to be connected to 1. So first I am connecting them together. And then this point can be connected to a common point, which is providing logic 1. Okay. So now the clock connections are to be in such a way that the output of one flip-flop becomes the clock of next flip-flop. Similarly here, the output of this flip-flop becomes the clock of next flip-flop. So now we can see that all 3 flip-flops are getting their clocks. LSB is getting the clock externally and MSB is getting the clock from the previous flip-flops output. So now displaying the count of the counter. So this point, similarly this point and the third one. At these 3 terminals, the count of the counter will be displayed here, but we have to keep in mind that this is QA, which is the LSB, and this is QB, and this is QC, which is MSB. But when we'll be writing the counting, then I will be using QC, QB and QA. So initially, when no clock pulse is applied, the output of all flip-flops is 0. Okay. Now I am going to provide the clock pulses. So if I provide clock pulse here, first clock pulse is being applied at the clock input of A flip-flop. So it is very much clear to me. T flip-flop, which will be getting the clock, will toggle its output. So I am providing the clock manually to A. So it will definitely toggle the output 0 to 1. So this 0 to 1 is negative transition, because it is 0 to 1 is positive transition. That means this is the transition from 0 to 1, which is referred as positive edge. Similarly, this 1 to 0 transition, this is 1, this is 0, this is referred as negative transition. So all my flip-flops are waiting for negative transitions. Wherever they will be getting the negative transition on their clock pulses, they will toggle the output. So this is positive transition, which is not the required transition. So B will remain in its original state. Similarly, C will remain in its original state. Then I provide the second clock pulse again here at A. Again, A will toggle the output. This 1 to 0 is negative transition. So this negative transition, this is generated here, negative transition. So this negative transition is detected by B flip-flop and it will toggle the output. So this 0 to 1, it is toggling its output. This 0 to 1 is positive edge. So for positive edge, C will not be getting the desired clock and it will remain in its previous state. Okay. Similarly, if we proceed further for the third pulse, again, A will toggle. This will be the positive transition. Required one is negative transition. So B cannot change, remain in its previous state. C cannot change, it remain in its previous state. Similarly, fourth pulse, again provided to A. A will again change its output. 1 to 0 is negative, negative. That means it is a desired transition. So B will also toggle. B also gets toggled. 1 to 0, again it is a negative transition. So C can also toggle. So C changes from 0 to 1. So this is also the negative transition, but there is no more flip-flop further connected to the output of C. So we can stop here and provide the next pulse. So for the fifth pulse, again, it is provided to A. This is 0 to 1, positive transition. If the transition is positive, no more further toggling can happen. That means B will remain 0, C will remain 1. Sixth pulse, again, A will toggle. 1 to 0 is negative transition. That means B can toggle, B will toggle. This 0 to 1 is positive transition. That means C cannot toggle. So C remains 1 state. Seventh pulse, 0 changes to 1. This is positive transition. So no more changes can take further. So the 1 remains 1, 1 remains 1. So we can check that the counting has started from 0, 0, 0 and it has reached 111. That means 0, 1, 2, 3, 4, 5, 6, 7. All 7 counting stages are available at the counter's output as and when the clocks are applied to the counter. And if you want to check what will happen when the 8th pulse is applied. So if I give 8th pulse, then this 1 will change to 0. This is negative transition. That means B can also change. So this is also negative transition. That means C can also change. Again, this is negative transition. So ultimately, the counter has reached the state from where it had started. That means it has reached 0 again. So 0, 1, 2, 3, 4, 5, 6, 7. And at 7, if you give another clock pulse, it will go back to the initial state. That means 0. So this is how a up counter can work in counting mode from 0 to 7. Similarly, if we are asked to design a counter which is having 16 stages in up mode, we have to simply add one more flip-flop to it and connect it in the same pattern, and it will become 4-bit counter, or you can say mode 16 counter. Okay. Similarly, mode 8 asynchronous down counter. So you can see that I have changed this negative edge. Now this is positive edge, and rest of the connections are very much the same. So all T inputs are connected to a common point and further connected to 1. Output of the flip-flop is connected to the clocks. So this completes the clock connections. All outputs are taken for the display. So here my count will be displayed. Okay, so this is count display. So all connections are complete, and you just need to check how it is functioning. So QC, QB and QA, initially when everything is 0 and you start applying the pulses, so this pulse is applied here. Okay, so a clock pulse is applied at the A flip-flop, then definitely it will toggle its output. So this 0 to 1 is positive transition, and now you can see that all flip-flops require positive transition for their operation. That means this is a desired transition, that means B can also toggle. So B also toggle. This is again the desired transition, 0 to 1 positive transition, so C can also toggle. So you can see that in up counter, the next stage of 0, we got 0, 0, 1 after 0, 0. But in case of a down counter, we are getting 1, 1, 1 after 0, 0. That means next counting state of 0 is 7. Similarly, if I provide next second pulse again to this A flip-flop, then again A will toggle. This is 1 to 0 transition, which is negative transition, which is not desired. So if it is not desired, B will not change, B will remain 1, C will remain 1. So this is the counting flow. You can check that this is equivalent to 0, this is equivalent to 7, this is equivalent to 6, and you can proceed further. Similarly, you can, if you reach 7, then it will go from 6, 5, 4, 3, 2, 1, and it will reach 0, 0, 1. And then if you apply the 8th pulse, then again 1 to 0 will be the negative transition. So B and C cannot change, so they will remain 0. That means again the 8th pulse you will be reaching the state from where you started. That means only 8 unique stages are possible in the mode 8 counter. That means if we are connecting 3 flip-flops in this fashion using positive edge clocks, then only 8 stages can be available. Okay, let's proceed further. So mode 8 asynchronous down counter, another method. So here you can see that now I'm going to design a down counter, but I'm not going to use positive edge. I'm using negative edge. So if I'm using negative edge, then the clock connections cannot be QA to clock. It will be QA bar to clock. Similarly from here, QB bar to clock. Why? Because if QA is generating positive transition, then QA bar will be generating negative transition. That means whenever this QA is functioning as positive edge, QA bar will be delivering negative edge. If QA is delivering negative edge, then QA bar will be delivering positive edge. That means if the positive edge requirement is not met by this QA, if it instead of using the positive edge triggered T flip-flops, I am connecting the outputs from the inverted output of the previous flip-flop. Okay, rest of the connections are exactly same. That means all T inputs are connected to a common point, and again all these will be connected to 1, and rest of the things, that means outputs, can be taken for display. So here the count can be displayed. Okay, so this is mode 8 asynchronous down counter. That means if I can design down counter using negative edge, that means I can also design up counter using positive edge. That means if this was the down counter using positive edge, I can design up counter from here as well by reversing the connection. That means if I connect this QB to clock, similarly QA bar to clock, if I make these connections, then using this positive edge T flip-flop, I can design up counter as well. Okay, so now clock is not a foundation for me. I am very much aware that clock can be static one. That means on a single clock, I can design both the operations up and down by making the clock connections reverse. If I use QB and QA for further clock connections, then it will be up counter. if I use QA bar and QB bar, it will prepare down counter. So let's proceed further. So that means if I use a multiplexer in between these circuits, then I can design both the counters in a single circuit by using the select line of the counter. Okay. Now coming to the next concept, which is very much important, mode 10 counter or a decade counter. Okay. So mode 10 counter or a decade counter means the counter which is having 10 stages. So mode 10 means 10 stages. Okay. So 10 stages will be 0 to 9. So this 0 to 9, we are very much familiar that these 0 to 9 are also available in decimal form. So that means this counter can also be named as decimal counter. And decimal is directly related to BCD. That means the same counter can also be referred as BCD counter. So if you're asked to design a mode 10 counter, decade counter, decimal counter, BCD counter, all four are same. Okay. But the thing to be noticed here is that this mode is not equal to 2 raised to power n. Okay. If the mode is equal to 2 raised to power n, we have seen that if 3 flip-flops are arranged in the same fashion, then we saw that the counting starts from 000 and it goes to 111. That means all full scale counting from 0 to 7 is happening. But if I have to truncate the counting, that means I am stopping somewhere in the middle of the range, of the complete range. That means if 4 flip-flops are connected, then I am very much aware. Then if I make the normal connections, it will start from 0, 0, 0, 0 and it will go till 1, 1, 1, 1. That means it will count from 0 to 15. So if I make usual connections, then I will making the mode 16 counter, which is the first step of designing this mode 10 as well. So if I need to prepare mode 10, first mode 16 will be prepared. Okay. Then I will take some decisions, make some standby arrangements so that the counting does not go beyond 9. Okay. Which will be definitely, if I do not make any corrective arrangements, then definitely after 9 I will be getting 10, 11, 12. Okay, but I am not interested in 10, 11, 12 and I want 10 to become 0 because I am only interested in counting till 10 stages. 10 stages means 0 to 9. So let's see how this can happen. The basic things which I am very much aware, I am making those connections first. That means output of the flip-flop will become the clock of next flip-flop. Output of this flip-flop becomes the clock of next flip-flop. Output of this flip-flop becomes clock of next flip-flop. This is very much the same. And then all the T flip-flops inputs are going to be connected to a common point. Similarly here. And you can connect it to logic 1. And you have to display the output as well. On the lower side, I will be making the connections. So I am taking these display outputs on the upper side. So on these terminals, I can get my count displayed. Okay. So the count of the counter will be displayed on these 4 terminals. But this is very much clear to me that this is not mode 10 counter because this is a normal counting arrangement. So it will count from 0, 0, 0, 0 to 1, 1, 1, 1. That means 0 to 15. That means currently it is mode 16, not mode 10. So let's make some arrangement. I'll be requiring some space here, so better to erase it. So what is the logic here? Now my counter will be 0, counting from 0, 0, 0, 0 to 1, 0, 0, 1. These are the required stages. And 1, 0, 1, 0 not required. So this 1, 0, 1, 0 has to convert into 0, 0, 0, 0 if I need my counter to be in count till 9 only. Okay, that means 10 has to change to 0 on its own. Okay, so how this is going to happen? That means abruptly I want all the flip-flops to make their output 0 if a condition is met. So what is that condition? If I label this as the flip-flop outputs, so ultimately because we are going to get these count on the display terminals QA, QB, QC, QD. Okay, and if I label them as Q, QD, QC, QB, QA, then I can see that if QD and QB equal to 1, okay, if QD and QB are simultaneously 1, then the next stage should not be 10. This 10 should convert into 0. So how this is going to happen? Because output cannot control the flip-flops behavior. We have to make some extra arrangement. For that, we will be using the additional asynchronous inputs which are available with the flip-flop, which are preset and clear. So preset is used to make the flip-flops output permanently high, and clear is used to make the flip-flops output permanently low. As long as preset and clear are activated, these outputs are going to remain permanently, and if you disable them, then normal flip-flop operation can perform. So these are the locations of the clear inputs. And another important thing about these clear inputs are these clear inputs. Just a second. So these clear inputs will be connected to a common point, and I will be using this terminal to activate all the clear inputs. So this bubble is indicating that these are active low inputs. That means these will be activated if they get 0 signal. So to disable them, I will be sending a 1, and to make them work, I need a 0 on all the clear terminals. Okay, so this is my task now. That means I have to generate a 0 to activate these clear signals when my QD and QB is equal to 1. And when this QD and QB will be equal to 1, when the counter will reach 1010. So if I use a NAND gate, okay, and make these connections, this QD and this QB, both these 1 inputs reach the NAND gate, then definitely this NAND gate will produce a 0. Okay, this NAND gate will produce a 0, and this 0 can be used to clear all the flip-flops. I will be connecting this 0 output to all the clear inputs of all 4 flip-flops. Okay, that means, summarizing the operation again, the counter will start counting from 0, 1. And why this counting is possible from 0 to 1? Because at that point of time, all clears are deactivated. Why they are deactivated? Because these are going to be activated only when QD and QB are simultaneously 1. So for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you write counting from 0 to 9, you can check that QD and QB are not simultaneously 1. So if they are not simultaneously 1, then definitely the NAND output cannot be 0. So if at least a single 0 is there, the NAND output will be 1, and this 1 will disable all clear inputs as long as my counter is counting from 0 to 9. But as soon as the counter reaches 10, then this 1010, 10 means 1010. That means QD and QB are 1. So if QD and QB are 1, okay, then this NAND gate will generate a 0 output, and this 0 output will clear all the flip-flops. That means all flip-flops will generate a 0 output. That means all flip-flop will abruptly give a 0 output. That means 10 will change into 0. So counter cannot go beyond 9. And this 10 to 0 transition will be so fast that it cannot be recognized by a human eye. It will be in some microseconds, if depending on the clock speed. Okay, so this is how we can design counter in up mode, down mode, using any clock, and a counter which can count in truncated mode. That means we are not counting up to the full scale value, because for these 4 flip-flop arrangement, the full scale value would have been 1, 1, 1, 1, 15. Okay, so this is about the counters. Thank you very much. So this concept can also be extended, as I already told you, that it can also be extended to the up-down counters as well. So in next lecture, we'll be covering the complex topic from unit 4.